Hello friend, now we are here for a new video and this is all about the combination of lenses. So in this video friends, we will learn the following topics. First is combination of lenses. So in the section of combination of lenses, we will learn about the equivalent focal length, what will be the equivalent power and what will be the magnification in that scenario. This section is applicable when two thin lenses are coaxially placed. So when two convex lenses are combined, when two concave lenses are combined, when one convex and concave lenses are combined. So we will see all this scenario. Again, we will see that how we calculate the maximum or the minimum focal length in case of combination of two lenses. What will be the maximum focal length and what will be the minimum focal length? When two lenses are placed coaxially at a distance d, then we will calculate the equivalent focal length and position of the equivalent lens. So basically we have divided this whole video into two parts. First is placing of two thin coaxial lens at in the contact, and second when they are placed coaxially at a distance d. So please watch it from start to end. Subscribe it, like it, share it, and press the bell icon also. Thank you and happy learning. In this video, we will learn about combination of lenses. And it is true for thin lenses are placed coaxially. So when several lenses or mirror are used coaxially, the image formation is considered one after another in steps. So we have to consider first the image formation by the first lens, and then the image by first lens will serve as a object, in fact virtual object, for the second lens, and the image formed by second lens acts as an object for third one, and so on. So if there are multiple lenses placed, then the image formed by first lens will serve as a virtual object for the second lens, and the image formed by second lens will serve as a virtual object for the third lens, and so on. So first we will prove this thing and then we will see different examples of this. So I have taken here a convex lens. You can take any other lens, but drawing ray diagram for convex lens is easy. So I took two convex lens L1 and L2 and place them coaxially. It is important to note that this is true only for thin lens. So I have taken two thin lenses L1 and L2, and the focal length of these two lenses are f1 and f2 respectively. The optical center of first lens is C1 and optical center of second lens is C2. A is the midpoint of these two lenses. Now consider an object O, then the ray diagram comes from this object and it refracts from the first lens. If the second lens was not there, then the image would have been formed at the point I1. So this I1 will serve as a virtual object for the second lens, and the second lens in turn refract these rays to converge at the point I have denoted by I. So basically U is the object distance, and we take the object distance from the first lens, that is C1 is equal to U. Now the image formed by first lens is also taken from the optical center of first lens. So C1 I1 is the image formation by the first lens, and if you see here for the second lens, this C2 I1 is the object distance and C2 I is the image distance. So first I will write the object distance and image distance for both lenses. So for first lens, object distance OC1 is equal to U, and image distance is equal to C1 I1, and we call it V1. For second lens, object distance is C2 I1 is object distance, I just note it OD, and C2 I is image distance. So we just apply the lens formula for first lens, and we see that if we apply the lens formula for first lens, considering the second lens to be absent, then the equation will be 1 by v minus 1 by u is equal to 1 by f. And here, so our lens formula is 1 by v minus 1 by u is equal to 1 by f, and the object distance is u, and the image is v1. So 1 by v1 minus 1 by u is equal to 1 by f1. Now if we put the values, then we see that 1 by v1 is equal to 1 by c1 I1 for first lens minus 1 by c1o is equal to 1 by f1. So this is basically our equation 1, as c1 I1 is the image distance, c1o is the object distance. Now this image I1 serves as a virtual object for second lens. So for the second lens, we will write equation again 1 by v minus 1 by u is equal to 1 by f, and here the focal length is f2. So the final image distance is v, and so if I write equation, v is equal to 1 by c2i minus, and image distance and the object distance is c2i1, and focal length is 1 by f2. So this is our equation 2. So basically we have got two equations. Now we have to understand the focal length of this combination. So this light ray is refracted from the both lenses, and to calculate the equivalent focal length, we have to consider the contribution of both lenses in the refraction of light ray. So for this we will add these two equations 1 and 2. So if we add these two equations, then what we will get? We will get 1 by c2i plus 1 by c1 I1 minus 1 by c2 I1 minus 1 by c1o is equal to 1 by f1 plus 1 by f2. So this is our equation 3. Now, as I have already told that this equation is valid only for thin lens, and lens are placed coaxially. So for thin lens, so c1 I1 is equal to c2 I1. Again, AO, that is the object distance from this equivalent lens. We are considering a equivalent lens to be placed at this point having A as its optical center. So the object distance from point A, that is AO, is equal to C1O, and it is equal to C2O, because we are considering these two lenses are thin. So AO is equal to C1O, and it is equal to U, and similarly C2I is equal to AI, like the image distance from this optical center of second lens is equal to image distance from optical center of equivalent lens, and it is equal to V. So if we do this approximation, then we get 1 by C2I plus, and this term will get cancelled out. So 1 by C2I plus minus 1 by C1O is equal to 1 by F1 plus 1 by F2. So C2I is equal to 1 by AI, and C1O is 1 by AO is equal to 1 by F1 plus 1 by F2. Now for this equivalent lens, AI is the image distance, AO is the object distance. So we may replace it by 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2, and as we know from the lens formula, we may write 1 by V minus 1 by U is equal to 1 by F equivalent. So 1 by F equivalent is equal to 1 by F1 plus 1 by F2. So on adding these two terms, we get 1 by F is equal to 1 by F1 plus 1 by F2. So if two lenses are added, then, and if two lenses are thin and placed coaxially, then 1 by focal length of equivalent lens is equal to 1 by focal length of individual lenses. So 1 by F1 plus 1 by F2. And we can extend this formula also, like instead of two lenses, if there are more than two lenses, then 1 by F equivalent is equal to 1 by F1 plus 1 by F2 plus 1 by F3 and so on. Again, while applying this formula, you have to consider the sign convention also. While applying this formula, you have to make sure that F convex should be positive while F concave should be negative. Again, as we know that the power is the inverse of focal length, so P is equal to P1 plus P2 plus P3 and so on. Two or more than two lenses are placed coaxially, and if all lenses are thin, then the power of equivalent lens will simply the addition of power of individual lenses. Now we will calculate the total magnification of this system. So the total magnification will be given by, as we know that magnification is the height of image divided by height of object. So the magnification is I divided by O. Now we may write this term in this way, like I by O is equal to I1 by O into I2 by I1 into I3 by I2 and so on. So if there are multiple lenses placed, then as we know that the image of first lens will serve as an object of second lens. So for the second lens, I1 will be the object height, while its image height will be I2, which will again serve as an object for the third lens and so on. So these are basically the magnifications of each term. So the magnification of system or the equivalent magnification is the multiplication of individual magnification. So if multiple lenses are placed coaxially and if all lenses are thin, then this is the relation of their focal length, the power of the system as well as the magnification of the system. So for the two lenses, this combination will behave as a lens with focal length f is equal to f1 into f2 divided by f1 plus f2. If after calculation, if we get the net focal length or the equivalent focal length with a positive sign, then it clearly means that the equivalent length will work as a convex lens or convergent lens. And if after calculation we get the equivalent focal length in with negative sign, or we get the negative value of equivalent focal length, then it means the combined system will work as a divergent lens. So this is the basic concept about the combination of lens. And now we will apply this combination of lens in different situations. So when two convex lenses are combined, then as we know that the formula of equivalent focal length or the formula of focal length of an equivalent lens is given by f1 into f2 divided by f1 plus f2. And as both lenses are convex lens, so this will come with a positive sign, this will also come with a positive sign. So we have a positive value in the numerator and we have a positive value in the denominator. So in turn we get a positive term. So clearly positive term indicates that it will work as a convex lens. And again, if we write 1 by f equivalent is equal to 1 by f1 plus 1 by f2, then it clearly means that f equivalent is less than both f1 and f2. So it's less than f1 and f equivalent is less than f2. So the combination will behave as a convex lens with less focal length. And if we consider the power, then the power of equivalent lens is equal to P1 plus P2. So power of a convex lens comes with a positive sign, and power of a and the other lens is also convex, so it will also come with a positive sign. So clearly P equivalent is greater than P1 and P equivalent is greater than P2. So combination will behave as a convex lens having more power and less focal length. Now we will see the consideration that when the maximum focal length can be observed in case of equivalent lens. So suppose that the formula of equivalent lens is equal to f1 f2 divided by f1 plus f2. So for maximum f equivalent, so if we have to calculate the maximum f equivalent, the f1 plus f2 term, that is which is in the denominator, should be minimum. So f1 plus f2 should be minimum. And as we know from inequality that a plus b must be greater than and equal to twice square root ab. That is, the minimum value of a plus b will be achieved. So if we have to achieve the minimum value of a plus b, then it is possible only when when A is equal to B, and at that point A plus B minimum value is equal to twice square root AB. So if we apply the same concept here, then F1 plus F2 minimum value is equal to twice square root F1 F2, and it is possible only when F1 is equal to F2. So if we have liberty to choose the value of F1 and F2, then F equivalent maximum is possible only when F1 is equal to F2, and in this case F equivalent maximum will have value equal to F1 F2 divided by twice square root F1 F2, and it's equal to 1 by 2 square root F1 F2. So F equivalent max is equal to square root F1 F2 by 2. So considering F1 is equal to F2, as this is our condition, then it is equal to F1 by 2 is equal to F2 by 2. So the maximum value of combined focal length will be achieved when both focal lengths are same, and the maximum value is equal to half of the individual focal length. So now when the minimum value of focal length will be achieved, so the minimum value will be achieved when one term will very high in comparison to other. Like if F1 is very high greater than F2, or F2 is very high greater than F1, then the minimum value of equivalent focal length will be achieved. So for F1 is, so considering F1 is very high than F2, then we get F equivalent is equal to F1 F2 divided by F1 plus F2, and in this case it is F1 F2 divided by F1, as F1 is very high in comparison to F2. So in turn we get the equivalent focal length is equal to F2. So the equivalent focal length will be equal to or approximately equal to the smaller focal length. So when two convex lenses are combined, then the combination will behave as a convex lens having more power and the less focal length, and the maximum value of focal length is possible when the value of individual focal lengths are same, that is F1 is equal to F2, and in that case the equivalent focal length is equal to half of individual focal length, and the minimum value of focal length will be achieved, when one focal length or the focal length of one lens is very high in comparison to the second lens. And in this case the minimum value, and in this case the equivalent focal length is equal to or approximately equal to a smaller focal length. So this is the concept when the two convex lenses are combined. Now consider the case when two concave lenses are combined. So if you combine two concave lenses, what it means? It means we are combining two divergent lenses. So clearly the diverging power of lens increases, because the diverging powers of one lens will augmented by the diverging powers of other lens. So basically the net diverging power will increases. We will see also it through the formula. So clearly the focal length is equal to, or the equivalent focal length is equal to F1 F2 divided by F1 plus F2. We have already learned this formula. Now for this divergent lens, F1 is equal to, F1 comes with negative sign and F2 also comes with negative sign, or we may say that the power of both lenses are negative. So as F1 is negative, F2 is negative, so we are multiplying some negative quantity, two negative quantity in the numerator, and adding two negative quantities in denominator. So basically in numerator we have one positive value, and in denominator we have a negative value. So we get a negative value, net negative value. That means we get a net divergent lens. So basically when two concave lenses are combined, we get a concave lens, and the combination have less focal length and more power. So if you see the focal length, I have already discussed this thing, that in this case F equivalent must be less than F1 or F2, and the maximum value of F equivalent is equal to, that is F equivalent is equal to F1 by 2 or F2 by 2 when F1 is equal to F2. So clearly the focal length having the combination has less focal length, and as power is inversely proportional to focal length, so we will have more power. Now we'll see next case, and next case is very interesting, that when we combine one concave and convex lens. So when convex and concave lenses are combined, then we get either convergent lens or divergent lens, or lens having zero converging or diverging power. So we are considering the case when we are taking one biconvex lens and one biconcave lens. So this is our equi or biconvex lens, this is our biconcave lens, and the focal length of formula, that is F equivalent, is equal to F1 F2 divided by F1 plus F2. Now F1 is the convex lens, so F1 must have positive sign. The power of convex lens must be positive, and similarly if you see here, F2 comes with a negative sign, so power of F2 is equal to a negative value. So basically we are in the numerator, we are multiplying one positive quantity with one negative quantity, and denominator we are adding one positive with a negative value. So in numerator we have a negative quantity, in denominator we have either positive or negative. So we have either positive or negative. Now if F1 is greater than F2, that is in denominator the positive is greater than the negative. So what it will be F equivalent is equal to minus divided by plus, that is equal to minus. So the net will act as a divergent lens, and this is the example which is given here. If you see this figure, then the light ray, it diverges from the object. The convex lens having focal length F1 converges it. So if you draw so this is basically our normal line for this surface, and if you see here, for this line angle of incidence is this I1, this angle of this is our angle of refraction. So clearly R is less than I, as the light ray is moving from a rarer to denser medium. So basically this is our medium, suppose it is a rarer medium, and this is lens material which is denser medium. So clearly the light ray will move towards the normal line, so it will converge the light ray. Now when light ray goes to the divergent lens L2 having focal length F2, then it will diverge, and the net result in this case is the divergence of lens. So if you see here, the image formed by this this lens L1 is I1. So this is basically the virtual image, and it will serve as a virtual object for lens L2. So for lens L1, it will form a it will converge the light ray, while the lens L2 will diverge the light ray, and the net result is the divergence of light ray. So it means if you see this figure, then you may clearly infer that F1 must be greater than F2, or the power of first lens will be less than power of second lens, or whoever have the more power will dominate. So clearly here F equivalent will be less. So it's written here, if you see here, that for opposite lens and different focal length, resultant focal length will be same nature as that of lens of shorter focal length or the greater power, but its magnitude will be more than that of the shorter focal length. For this figure B, we have F1 greater than F2, so F equivalent will clearly have the nature equal to lens L2. So clearly, as L2 is of diverging nature, then the equivalent focal length will have diverging nature. These are the basic concepts. Now we will see that when F1 is less than F2, so we will see the case f1 is less than f2. And if you see this equation, then on the numerator we have negative sign, and in the denominator we also will have negative sign, as f1 is less than f2. And clearly the resultant comes with a positive sign. So f equivalent comes with positive sign, and positive signs means it will work as a convergent lens. So the equivalent lens in this scenario will work as convergent lens, and it will converge the light rays. So if you see this figure, then after the refraction from the first lens L1, the virtual image will form at the point I1. So if this lens L2 was not there, then this light ray would have been converged at the point I1. Now, as this light ray are not converging at this point I1, so it will serve as a virtual object for this lens L2, and this lens L2 will diverge this light ray, and in turn the whole system will converge the light ray at the point I. So clearly, if you see this figure, then this system works as a convergent lens. So as F equivalent is positive, then this system works as a convergent lens. When one convex and concave lens are combined, then as a system they will either work as a convergent lens, they will work as a divergent lens. So when they will work as convergent lens, they will work as convergent lens when the focal length of convex lens will be less than the focal length of concave lens, and if the focal length of concave lens will be less than the focal length of convex lens, then they will work as a divergent lens. The next situation arises when the focal length of both lenses are same. So when two lenses are of equal focal length but of opposite nature, and they are placed in contact with each other, then the combination will behave as a plain glass plate. So if you see this figure, then the combination behaves as a plain glass plate, as the parallel beam of light coming from infinity will move undeviated. Clearly in this case, the focal length of combination is infinity and the power of combination is equal to 0. So the system will behave as a plain glass plate. They will neither converge the light ray nor they will diverge the light ray. So if you see this equation, then F is equal to F1 F2 divided by F1 plus F2. And clearly, as F1 and F2 are equal in magnitude but opposite in direction, so in numerator we have minus plus, in denominator we have plus minus, and these two minus plus are equal. So in denominator we have a term equal to 0, and in numerator we have negative quantity, so clearly it is equal to infinity, and so F equivalent is equal to infinity and power equivalent is equal to 0. So this is the case when the system work or behave as a plain glass plate. Now we will move to next concept. Next concept is when two lenses are placed coaxially at a distance d from each other. So this is also one of the important formula. Here we have to calculate the equivalent focal length of two lenses when they are placed at a distance d from each other. And here the figure has been drawn. Lens L1 has a focal length equal to f1 and its optical center is c1, while the lens L2 has a focal length f2 and optical center c2. Now, these two lenses or this combination of lenses are placed coaxially to each other at a distance d from each other. Now, a parallel beam of light ray comes, and this parallel beam of light will focus at a point I. And this parallel beam of light will focus at a point I. So we have to find out the equivalent lens, or we have to if we have to replace these two lenses with a single lens, then what will be the location of that lens, what will be the equivalent focal length of that lens? We will learn these two concepts in this video. So this is the image formed by this combination of lens I. So suppose here the light ray comes, and after the refraction from this first lens, it moves in this direction, and it is supposed to converge at a point I1. Now the lens L2 comes in picture, and because of this the light ray again refract and converge at the point I. So clearly the image is formed at the point I. Now we have to first calculate the equivalent focal length of this system, and the equivalent focal length of this system is given by the formula 1 by f equivalent is equal to 1 by f1 plus 1 by f2 minus d divided by f1 f2. So I am giving you this formula without the proof. So you just learn this formula and apply it for the numericals. So basically this is important for your competitive examinations. It is 1 by f equivalent is equal to 1 by f1 plus 1 by f2 minus d divided by f1 plus f2. And secondly, you have to note that you have to apply the formula along with the sign. Like if it is a convex lens, then the value of focal length f1 or f2 comes with a positive sign, while if it is diverging lens or concave lens, then it comes with a negative sign. So clearly you have to apply these two sign conventions also while calculating the value of equivalent focal length. So what will be the position of that lens? So the position of that lens will be decided from this second lens L2, and we denote it by the term delta. So delta is equal to df equivalent by f1, and this is also very important formula, that the length of equivalent lens from second lens is given by the formula df equivalent divided by f1. So if we expand this, then 1 by f equivalent is equal to 1 by f1 plus 1 by f2 minus d divided by f1 f2. If we take LCM of it, then f1 f2 plus f1 minus d, and from there we get f equivalent is equal to f1 f2 divided by f1 plus f2 minus d. So clearly this is the value of equivalent focal length. Now as we know that the focal length is inversely proportional to power, so P equivalent or P net is equal to P1 plus P2 minus D divided by 1 by f1 into 1 by f2. So clearly P1 plus P2 minus D P1 P2. So this is the value of equivalent power, that is P1 plus P2 minus D P1 P2. And for equal focal length, that is if we take f1 is equal to f2, then we get a 1 by f equivalent is equal to 1 by f plus 1 by f minus d by f square. So we get it's equal to 2f minus d divided by f square, and from there we get f equivalent is equal to f square divided by 2f minus d. So this is the value of f equivalent. You can get it from by just putting the f1 equal to f2 in this formula. Now what is the net power? Net power, just putting p1 is equal to p2 if we have equal power of both lenses, and in this way we get p net is equal to 2p minus dp square. So you just keep this formula in your mind. Again, while applying this formula, you just take sign in consideration. Suppose this first lens is concave lens. For this first lens is concave lens, then f1 comes with negative sign, and the second lens is a convex lens, then f2 comes with positive sign. If both lenses are concave lens, then you should take f1 and f2 both with a negative sign. So whatever is the lens, you just take sign accordingly.